So, hey everyone, hope you're all doing well. So, DeepSeek's reasoning model is out, and everybody in the AI community is basically talking about this, how amazing it is, and how it compares with OpenAI's O1 for reasoning. So, I wanted to put this to test myself. So, I used to watch this computer vision lecture, and so one of the best places if you want to learn computer vision is this playlist by Professor Sri Nair. And so I was watching this video lecture on computer vision, on camera calibration. So wherein Professor Sri Nair talks about the various steps you need in camera calibration and so on. And so everything was going fine, and he would explain this in great steps. So there was one lecture here, this estimating fundamental matrix lecture, right? So what Professor Srinair would do there is that he would basically explain, he would basically say that solving for f, find the least square solution for the fundamental matrix f. Then he would post this as a constraint least squares problem. And then he would tell that just like how he had solved projection matrix during and then during camera calibration or homography matrix for image stitching, he would just say that rearrange f to form the fundamental matrix f. And after this, he would just go on to the next step. Like you would just say that, oh, that's it. You had found f right there, and it's okay from his perspective because he had apparently already covered this in another lecture here, which is on image stitching. So he would basically have almost the exact kind of equation when finding the homography. He would have it here as AH equals 0, such that h squared normal of h squared equals 1. And he would go in detail and show that how this can be posed as a constraint least squares problem, and then he would also like show how he would kind of do that, and then he would like have this minimization equation here, and then he would also say how using the SVD this whole solution can be obtained. Basically, like putting this as an eigenvalue problem, and then computing the SVD, and so on. So the thing is that for me, when I was going through the lecture for computing fundamental matrix, I had to go back and forth and see, okay, how was this solution done, and then go back here and then kind of understand that, okay, this is how it's done, and so on. So what would have been amazing is that if I could just kind of take a screenshot and ask say like AI, like either ChatGPT or right now O1 or even DeepSeek, and see how is this actually done, right? So this is what I want to test out today with DeepSeek, especially given that this is a reasoning model, and this is not an easy problem, right? Like you have to go and then you have to know the subject, and you have to like go a little bit back and forth, and then this is where the true AI models, one of the ways wherein like AI could have really a huge impact. So what I'm going to do is that I already taken a screenshot of that, so I'm going to go to DeepSeek. So this is DeepSeek's website. So you can just go to chat.deepseek.com, and what's amazing is that it's free, and it's also under MIT license. And if you want to activate the reasoning model, so you first have to click on Deep Think. So that's what will activate the reasoning model. And then what I'm going to do is that I'm going to attach this. So right now it only supports image from images. It's not a full vision model. It only like supports text extraction from images. But either ways, let me go and upload this image, and then let's see what it's actually able to say. So I'm uploading the image which I just took a screenshot of, And so basically the one wherein like Professor um, um, Sri Nair explains how he obtains the fundamental matrix. Can you, first, I'm not even going to give any context, so I'm just going to ask, can you explain this image? Okay, just what is in the, can you explain what's in this image? So it just says that, okay, I've uploaded a screenshot, but look at what's going on here. It's amazing, right? And look at the speed. That's like super amazing. So let's see what it's, and I have not given any context so far. This is just absolutely brilliant, right? Just see what's, it says solving fundamental matrix in computer vision. So it's also saying that the image explains the process of solving for the fundamental matrix F in computer vision, which encodes the geometric relations between two views of a scene, epipolar geometry. That is absolutely correct. And then the key concepts, it says that the objective is find F such that the linear equation AF equals 0. And then A is derived from the point correspondences. I never mentioned anything about point correspondences, the pair of matching points. This is absolutely, this is what it's kind of, it's what is happening. And then it also talks about the epipolar constraint. And then it also says that minimize AF squared, least squares error, subject to the constraint that F squared equals 1. And if you remember, this is exactly what it is, right? This is the constrained least squares, linear least squares problem. And then you saw from the second lecture that computing the eigenvector of A transpose A corresponding to the smallest eigenvalue via singular value decomposition. This is what I saw in the second lecture. And just imagine, I had to go to a completely different lecture and then understand the steps here and then do this. So then he also talks about, I think this is already there in the screenshot, connection to other problems, projection matrix, camera calibration, homography matrix, image stitching, and so on. And so basically it's given me the full detail here. So let me also ask, what is the algorithm, and can you explain in steps, so that let's see how well it's doing in the context. So this is what the real thinking models is. What is amazing, it's that it's able to like just so quickly do it, right? So it's basically thinking right now, and then it's coming up with the steps needed to do this. So this is also important if I want to implement this as an algorithm. Professor Srinair's lectures are excellent, but implementation wise, it's still there. So let's just wait and see what it's giving. It's pretty, and what's even amazing, it's that it's not just giving the answer, but it's also like rendering this as equations and then putting it up. And this is amazing. So let's go back and see here, right? So algorithm steps. Yes, this is really the actual, this is, if you're in computer vision, you would have known these, right? Collect point correspondences, obtain at least 8, because homography, you need at least 8 points. And then consign the design matrix A for each correspondence, use the epipolar constraint so that you get this huge equation. This is what Professor Srinair also had in his video. And then solve the constraint least squares, and this is you can do this using the SVD, singular value decomposition. It's absolutely right. And S, the solution F is the last column of V. This is also right. This corresponds to the smallest eigen singular value, and form the fundamental matrix F. Reshape the 9 into 3 by 3 matrix. That is true. Enforce the rank 2 constraint, so that so this is usually a practical step that is done. So only if you're actually like coding it, you would actually know this part. So what you would do is that you would set this to actually 0, even though it's like small, so that you enforce that this is a rank 2 matrix, and then reconstruct F using the modified singular values. So using how, this is absolutely what happens when you do this. So I want to go one step further. Can you also generate Python code for this? So let's see how that's going to happen. This is amazing. Stereo vision, structure of motion. This is the basics of one of the base things that happens in computer vision. So it's still thinking on how it's wants to do things. So that's pretty nice. And what's nice is I can see how it's thinking So if I'll go back to it, it says, but wait, you have to do this and then do that. So it's like constantly going back and forth. So I was watching some videos on this, and then people are saying that this uses purely reinforcement learning, and it's can kind of shift back things a little bit, wherein you don't need these like this asked whether like you need the supervised linear supervised like RLHF. Instead of that, this goes directly to like pure reinforcement learning. So let me go back from, and it's, see, for real application use ransack, that's also nice. So let me go to the top and then go back here. So first I want to see how it's thinking, right? If you see here, um, so it says, okay, I need to generate Python code for computing the fundamental matrix using the 8-point algorithm described. Let me start by recalling the steps from the previous explanation. First, the user needs to input points correspondences, next normalization of point, then constructing the design matrix A. Once A is built, perform SVD, and then the rank 2 constraint. This is what it basically said in the previous kind of steps. Then denormalize F using the normalization matrices, return F. Now, handling edge cases. So what if they're exactly, this is also important because you would want to have these in your code, especially the edge cases. So then it also talks about some potential issues that could happen. And then testing the code. Maybe it actually is, it's testing the code, maybe with synthetic points. That's awesome. For example, if two images are related by a fundamental matrix, the code should recover it. So, and then it says, wait, but how to generate synthetic correspondences? This is what is really, I mean, I've never seen something like this in other models. It's like thinking to itself. It's actually thinking. It's like, wait, but how to generate synthetic correspondences? That might be beyond the current scope. The code should just take points 1 and points 2 as input. Now, putting it all together, I mean, I don't know if this is what it's actually doing behind the scenes, but it's nice to see that like this is the process. At least it's what it's there. So now putting it all together, first the normalization function. Let's create a helper function to compute the normalization matrix, and then build matrix A for each pair of normalized points. Create a row, and then it's also saying, so the row is this, and then it says, yes, that's correct. It's like as though it's talking to itself, just like how I'm talking to myself right now. And so the code for A should be like how it kind of puts a pseudocode here, and then does the whole thing. And then again, see here, now code example. But wait, the normalization matrices T1 and T2 are affine transformation. The normalization is done for each point xy. The normalized point is a T transpose a T. So T is a 3x3 matrix. So it goes on further to kind of like does the whole process. So it's like constantly going back and forth, and it's thinking this way, and until finally it arrives at, and then again a lot of but waits and so on, and suppose and so on. This is also interesting to see how. So Notebook LM, I would like to relate this to Notebook LM, is that it created this whole bus because it was so natural and explaining things. So when somebody is like reads this process, you could see how the AI model is actually like thinking, so on. So then it has Python and define compute fundamental matrix and so on. So I think the full code is here, and it also has like the SVD, and then the normalization part because of the scale. So then it also says how you can actually use this in here. So overall, I feel that, I mean, this is more than what I was hoping for, and like now I see why like the AI community is so excited with the DeepSeek model, and also like from what I've been seeing and reading, it's a free under MIT license, DeepSeek's MIT license, and also heard that, and it uses like mostly like reinforcement learning, and as opposed to like supervised fine tuning, and also what I heard is that this is also developed at a fraction of a cost when compared to like other big players like Claude or OpenAI and so on. So if this is what today is possible, I mean, things are just getting absolutely more and more crazy and amazing. So again, looking forward to more. So that's it for today.